Finally, I would like to invite and welcome our chair for this session, Ginestra Bianconi, who I presume don't have to introduce very much because she already gave a very nice talk here at the MECO. She is from University Queen Mary, London, and please, it's over to you.
Yes, welcome to the first afternoon session of today. We have a very comprehensive program with 3 talks on different subjects, but all very interesting. And then we will have the invited talk by Professor János Kertész. So we are still 2 minutes beyond the schedule. So let me just introduce Professor Claudius Gros, which will speak about autonomously adapting non-conserving sandpiles.
Okay, yes, thank you very much. And I will hopefully fully keep it relatively short. It is something relatively simple. It is a version of a sandpile model which we believe may be useful, especially for modeling brain dynamics. And I will explain why. So let me first recapitulate what is criticality, or why is it interesting. So at critical points in phase transition, we have power laws. And power laws are interesting because they are self-similar. That means the physical scales don't appear. That means even so you have a microscopic energy and length scale and time scales at the critical point that is all compressed into the parameter alpha, which is a scaling exponent. And therefore, we have a certain kind of universality. And that's the so that's the reason why we're interested in systems which have power law behavior. And you can observe them in quite a few environment in the brain. That's a lot of discussion. There in solar flares and earthquakes have been pointed out, for example, that some properties are power law-like. So there's a close connection between critical phenomena, well, self-organized criticality, and what it's called an absorbing phase transition. So an absorbing phase transition is a transition of an isolated system, so a system without contact with the environment, where you have 2 kinds of phases, an active phases here and a non-active phase here. So if you have some kind of active sites or components, nobody is active here, and when you start crossing the transition line, you have a finite density of active sites or cells, depending how you want to call them. And now you can come to a critical point by a mechanism which is involving timescale separation. So you have something happening slow and something happening fast. And fast is normally considered the dissipation. So if you have dissipation, you lose energy. You have less active site, for example, by particle removal, depending how you do that. And essentially, activity normally goes down when you have dissipation, and until you go to the critical point. Now, if you cross the critical point, well, in order to become active again, you have to do something. And if you do that very slow, for example, by adding particles, you have a mechanism that you close more and more to the critical point. And that is a mechanism behind what is called self-organized criticality, not in a closed system, but in an open system. I will explain it in the next slide. So there's an eternal debate what really self-organized means, because there's no system which is isolated and self-organized critical. You always need an interaction with the environment. And so in this sense, it's not 100% self-organized. But I will make strongly use here on this equivalent between absorbing phase transition and self-organized criticality by adapting some parameter, which I call a P or rho. So the classical sandpiles, many people probably have seen that, probably the vast majority. Many people have worked also with them by Bach, Tang, and Wiesenfeld. Just explain it again for the people who maybe forgot a little bit about it. So we have a very small table here. So we have open boundary condition, and we have stack of grains or energy. And when the stack is too high, well, it becomes unstable, it topples, but actually it doesn't topple only the upper grains, but everything, the whole stack is distributed. So this is too high because we have, we say we are toppling if we have 4 grains or more. And these 4 grains, which we have here, or these 4 energy points, are distributed here to the left and to the right. And so now we have 2 stacks which are active. Why they're active? Because they are too high. These 2 stacks are not active because they're not too high. And here it is z equals 4 is a critical height. So you continue the process. It is called an avalanche. And now what happens here? 2 goes to the middle, so from both sides. So you have 4 in the middle, and 2 on the left and the right fall off the table. And that is a dissipation. So in the third step, you have only 1 active column in the middle. You do it another time, and now you're inactive because this is a final configuration. It's an absorbing state because nothing is active and you cannot go on. So if you have a small driving, you add grains. So what you do is you do that until you got to an absorbing state, an inactive state. You add grains randomly. So you add grains slowly because you wait until the avalanche has stopped. So that is a classical sandpile model, and it is critical in the following sense. For example, if you calculate the size of the avalanche, so how many cells or how many grains are distributed, so how many cells are involved or how many grains are distributed, in large dimension, it scales like a power law, 1/3². And if you calculate the duration of the avalanches, how many steps you need, it scales also like a power law. Now, in the classical sandpile model, you are only critical if you're conserving. Namely, here you have 4 grains, and you exactly distribute 4 grains. But what if you are not conserving? So you have 4 grains here, but you distribute only 3 grains. So 2 to the right and 1 to the left. Now in this classical sandpile model, also in other sandpile models, you lose a criticality. So instead of a power law, you get exponential scaling. So you are not, criticality is 1-to-1 related to conserving. So but this conserving is of course very nicely in a theoretical model, but in many practical applications, you don't have anything conserving. For example, in the brain, the neural activity has nothing even remotely similar to being conserved. But nevertheless, you would like to model criticality in the brain if it's there by some kind of generalized sandpile model. So we considered a different sandpile model, which is depicted here. It's called autonomously adapting. It is very simple. You always distribute grains, either 2 or 3 grains, with either probability 1 minus p or p. So here we have a configuration, or 1 is the number of grains in the cells. Here we topple if you have 2 or more grains. And this is an active site. We don't care how high the cell is. So we don't care if there are 3, 4, or 10 grains. It doesn't matter. We distribute with the probability 1 minus p 2 grains randomly to nearest neighboring sites, and with the probability p 3 grains to neighboring sites. Could also be on the same site, could be on different. So in this example, we end up with an absorbing inactive state, and in this example, the avalanche goes on because we have another active site here which we could topple. So it's manifestly non-conserving because, well, brain it's non-conserved. But nevertheless, it has an absorbing phase transition, and one can calculate that. If we did that with numerical simulations, mostly in one-dimensional system and in two-dimensional systems, And you can do that using periodic boundary conditions, and the order parameter is in the density of active sites. So P is a probability to topple 3 sites, so three grains. And if P is larger, you get an active phase, and if P is small, you get an inactive phase. You get absorbing phase transition. And you don't have a runaway activity, because if you have too many active grains, well, you can maximally distribute 3. Now they have 4 lines here, actually. The red lines are for a 2-dimensional system. You have a critical probability of about 0.27, and here it's 0.7 for 1 dimension. Now, so this is a normal absorbing phase transition I also plotted, but we found a relatively interesting observation I will talk about now. They are metastable states. Now, what are these metastable states? These are pretty unusual for sandpiles, and let me explain. Now, the lattices we are considering here are bipartite lattices. So lattices with A sublattices and B sublattice. And when you're active on an A sublattice, you distribute all your sites, your grains to B sublattice and vice versa. And that is true for all sandpile models, the Mare models, the original sandpile models, all kind of version. If you consider bipartite lattices, you have a symmetry. Namely, if all active sites on an A sublattice, in the next time step, all active sites will be on the B sublattice and vice versa. And now, if you start with a configuration where the active sites are equally distributed on A and B sublattices, well, you normally expect them to remain there. But this is actually not the case. If you look at the Mare model, which is very similar, it's like the Bachmann and Wiesenfeld model, just with critical Z of 2. You see, if you look at the sites on the A sublattice on E, so what we call AB is here the density of active sites on a B sublattice on odd time scales, on an A sublattice in even time steps, and here vice versa. And you see that the sandpile models spontaneously break the AB sublattice symmetry. So after a certain time, all active sites are either on the A or on B sublattice and vice versa. And that is true if you do synchronous updating, which you normally do for all known sandpile models. Now, for our models, what is special is that the initial state where the AB sublattice symmetry is not broken is transiently stable, so it's metastable. In the Mare model, you decay very fast to the broken state. In our model, you take a long time to decay. So you have a metastable states, and these are states where the AB sublattice symmetry is not broken, and in the thermodynamic stable state, the symmetry is spontaneously broken. This, by the way, is an observation which I guess has not been made before, but maybe somebody knows better. And so we can take a closer look at these transient states. So we have them here, the symmetry is broken here, and there's a strong fluctuation here, whether the sites are the active sites are mostly on A or B sublattice, they're fluctuating. And when you have a close-up, you see these fluctuations are going on for a very long time until you break. You can actually make an experiment where you start from the symmetry broken state, then you add a disturbance, 5% of active sites on the wrong sublattice. Then the symmetry conserving state is recovered for a long time, metastable. So these are this is 1 million, so times 1 million time steps. So it's a long time. And until it gets spontaneously broken again. So this is something relatively new and interesting, and the significance of this metastable state is not yet clear. So then you can just calculate also critical exponent in a normal way. We have two order parameters. One is the density of active sites, which is scaling, and the other one is the density of grains, because the density of grains is self-organized and it's not fixed. So we have two order parameters, but we find them, these order parameters are coupled. So B and B tilde are always the same. And the interesting point about this model is that you can define an external field, which is very relevant for neural network modeling, because you're just adding grains. You cannot define this field as simple when you have conservation, because adding external grains changes your state. But since the density of grains is self-organized, you have an external field, and you also can calculate the waiting time distribution. I'm not going over that. And you can calculate critical exponents. I will do it a little bit fast here. And you find that you are in the directed percolation universality class. You can do it in 1D, you can do it in 2D. I will skip over that because I really want to make, as the last point, connection to modeling the brain. When in the brain, we have cells, and you are adding input from other, you receive input from other neurons until you are starting to fire. And this toppling event is like a spike in the brain, and the external field, which is important in neural modeling, are proportional to the inputs. So what we have here is, in the brain, we're getting input until the membrane potential crosses the threshold. We are toppling. And when we spike, it doesn't matter how much you cross the threshold. You just emit one spike, and this one feathers out to all the postsynaptic neurons. So we believe that there's no conservation here. We believe that this autonomously adapting sandpile model is a good starting point for modeling brain dynamics. So, not to remain in time, so just like want to say that we proposed a very simple model. It's a non-conserving. We found some interesting new phenomena, namely the AB sublattice symmetry breaking and the metastability, and we believe that this model is pretty good, or maybe a good starting point for modeling brain dynamics. Yes, thank you very much.
Thank you so much for the very interesting talk. We have maybe a little time for a question if somebody wants to ask. Let me check in the chat. There is. Does anybody have a question? Or I have a little one. You find this metastability phenomenon. Is there an interpretation in terms of, or general interpretation in terms of the neural network connection that you made?
Well, no, because in the neural system we don't have an AB sublattices. But just our point is we don't know yet which is the significance that we believe it influences the scaling to criticality, because that in the end, of course, you go to the thermodynamic state, but if you have this metastable states, you may converge much more slowly.
Okay. Okay. Thank you so much. So we move now. Thank you so much, and let's applaud. Let's move now to the next talk. The speaker is Beatriz Seoane, I hope I pronounced correctly, from the Complutense University of Madrid, and she will speak about COVID. So you can start sharing the screen.
Oh, yes.
She will speak about a scaling approach to estimate the COVID-19 infection fatality ratio by age. So it's a very timely
Hi, thank you. Good afternoon to everybody. I will be speaking about a very simple analysis I did some months ago, in which in discussion mainly with colleagues, I was trying to argue about what was the actual rate of infections in Europe, and in particular, what was the infection fatality ratio of COVID-19. So thank you to the organization for giving me the possibility to discuss it with even more colleagues. Okay, I hope you find it interesting. Okay, so the question about how deadly the COVID-19 disease has been, it has been quite elusive in the last month, as you all know. And the main difficulty to see how lethal is this disease is that we have quite a lot of problems to know how many infected people there have been. Okay, from the point of view of medicine, there is a well-defined parameter, which is the case fatality ratio, that gives the quotient between the number of deaths and the number of official cases that you know that pass the disease. The problem, at least with COVID-19, is that many of the patients suffer just mild or asymptomatic symptoms, so they are not detected. So we know that dying from COVID is a lot less probable than it will be what the case fatality ratio would tell us. And another reason, because it's not clear how deadly it is that not even the number of deaths are too reliable. We know from the deaths, I mean, with the comparison with the deaths in previous year, that this last spring, there was a lot more people dying than what the official statistics for COVID-19 says. In fact, I mean, one of the problems is that to be counted in the official statistics, you had to be tested positive for COVID-19. Many people died before, many people were not were not carried in the hospital. So it's hard to know how many people died directly linked to the disease, because also the sex test doesn't tell us that, because okay, there were also the people that died as a consequence of the situation, because the system was under stress, but not directly linked to the disease. So my proposal was to try to use the statistics for the deaths, the statistics in function of the age of the patients. And this, I did it for mainly two reasons that I will describe. The first one is that I believe that the missing number of deaths concerns more really people very old, so that the youngest patient, the deaths in the younger patients should be better counted. And in fact, here I can show you some data supporting this. Here I have data from England and also from Madrid, from the regional community of Madrid. And I just compared the records of the people that died, where the certificate had suspicion for COVID. They said that the symptomatology was related to, was similar to what expected for COVID-19, and the official death. So if I compare the excess between both of them, I find that below 80 years old, these numbers are similar. There's a bit higher the suspicion for COVID. And when we go above 80 years old, these two measures, they start to, I mean, they split up, even doubling the official numbers or even more. So I think we can trust better the data below this age. And also because the different countries, they have very different demographic pyramids. For instance, we have like two possible schema. If we consider Congo, we see that more than 30% of the population have less than 10 years old, and so few go above 80 years old. While if we look at Italy, we find that almost 20% of the citizens have more than 80 years old. So we expect a lot more deaths in Italy than we would expect in an African country, for instance, and the same can apply for different, for other populations. Okay, so what I propose is, okay, let's take the statistics of the deaths by age and normalize it by the number density of the population at this age. And when we do this, these are data from France, the evolution of the deaths by time. We see that the relative number of deaths in the 90s is much higher than those of the 20s, but by higher in several orders of magnitude. This is log scale. This is even clearer when we plot the same data, but against the ages of the patients, and we see that, okay, we observe essentially an exponential growth of the mortality with age, but also here I saw in different shades of color, the different times, and we essentially see curves that are parallel in time. So different times just differ by a proportionality constant. This can be easily understood in terms of asymptotic scaling relations. We expect that the number of deaths in a given age group should be proportional to the number of infected people in that group in a previous time. That will be actually a distribution on times, but just for the discussion, it doesn't really matter. And the proportionality factor will be nothing but the infection fatality ratio, the magnitude I wanted to compute. Okay, both this ratio and the number of infections are unknown, but we know that the number of infections for a given age, it should be essentially the weight of this group in the population of the total number of infected. And we can also assume that not all the age group are infected with the same probability, but if we assume that this probability doesn't change a lot with time, we can combine these both expressions, and we just get that the number of this normalized number of deaths, it should be proportional to the total number of infections in a given country. And the proportionality, it would be a magnitude related to the infection fatality rate that gives us how apparently it's more deadly one age than another one. Okay, one of the nice things of this expression is that, for instance, we expect that if we take the ratio between the deaths at a given age group and the deaths in another age group, we should expect something that is time independent, that gives us how more probable it is to die with an age than in another age group. Here I saw the same data for France, in which I divided the deaths by group by the number of the mortality rate from patients in the 50s, which will be just one here, and we see that the data collapse very well.
I'm sorry, Beatriz, you have just 2 minutes, 1 minute.
Oh, okay, I thought that I had it start. Okay, okay, we can do exactly the same with the different countries, and we also obtain very similar collapse functions. So with this, we can relate which is the number of infections in the different countries, and in particular, if we know what is the rate of infection in one country, as we knew in Spain, just from a survey of antibodies in the population, we can obtain which is the infection fatality rate as 8, and as I saw here, we obtain.
I'm sorry, I was confused. Now you have 10 minutes still.
Yes, that's what I was saying. I'm sorry. Or at least 5 minutes, I expect. Okay, so what we observe is that, okay, we have a growth that essentially grows as a pure exponential with a fatality that grows as a pure exponential with age, and that covers almost 5 orders of magnitude between the kids and the oldest people considered, people above 90 years old. Okay, this calculation was correct. We would expect that it would also be possible to, it could be applied to other countries, especially in first world, where there is health insurance. And I did it for using the death distribution by age in Geneva, and where there was also another serological surveys by age, and we obtained really perfectly compatible results, just reversing the infections from the number of the deaths. But when I tried to do the same thing with the mortality observed in New York City, with my parameters, I would expect that almost 60% of the population in New York had passed the disease, which we know it is not true because there were surveys done by the same moment at which they did this analysis, in which they had estimated that around 20% of the people had passed the disease. And this shows us nothing but that the lethality of the disease in New York City has been almost 3 times that what it was, for instance, in Spain or in Switzerland. And okay, we can do the same kind of calculations for other severity situations as function of age. And I just finished with a brief discussion about the consequences of this. Okay, we can establish a scaling relation between ages and countries because we expect all them to scale with the total number of infections. And beyond the actual numbers that we obtain, that will fluctuate because we don't really know what is the real number of infections at all. But what we can see, at least with this analysis, and this is true, is that we get this exponential growth of the mortality with age. And this means that if we want to make discussions, it doesn't really make sense to talk about a global infection fatality rate of the disease in the world, because different countries have very different populations, and we expect really sharp changes of this. For instance, just using this exponential growth that I fit in the data, if we neglected that there are other factors that affect, like different health systems and different socio-economical situations, we would expect that the mortality in Congo is 10 times lower than the mortality in the United States. And for instance, that the mortality in Italy should be much higher than in other countries. And I just finished with an announcement because I'm looking for a postdoc to come to my group in Madrid if someone is interested. Okay, feel free to apply and to ask for information. And that's, thank you very much.
Thank you. Let's thank Beatriz for this very interesting talk. So now we have plenty of time. Sorry for my confusion, for comments and questions.
Yeah, no, apologize. At that moment, I went too fast. I hope it was not. I'm sorry.
I see that there is an entry on the chat that Claudius Gros put, that he put a link to its interesting webpage of free interactive COVID-19 webpage for comparing and analyzing country region.
Okay, I cannot see the chat.
Yeah. Do you have a specific question, Claudius, also to add? Or?
Well, actually, everybody is wondering about the second wave. I mean, I think the analysis you presented was for the first wave, and the second wave, well, very few people are dying. So, do you have anything to say about that?
Well, I mean, my analysis is quite consistent about what we are observing in the second wave. Is that, I mean, the probability of dying. You see my screen still or not?
Sorry?
Do you see my screen?
No, I see you.
Oh, yeah, I'm sorry. Okay. At least with the numbers I was showing here, I mean, we know that in the second wave, the median of the patients is much lower than it was before.
But I've heard that this is not the whole explanation. Maybe you're right. I don't know. I just was reading that this is not explaining everything, but
well, I mean, and I think that many, well, at least the things that I have read, that they said that it's, okay, for sure there will be more, because at least in the oldest patient groups of people, there were a lot more people dying than what it could should have died because of lack of treatment. So this is for sure. But normally, the argument that they use, they tend to suppose that the fatality rate in younger people is a bit low. It's lower than for older people, but not the number of orders of magnitude that I'm showing here. I mean, I haven't that, but that's true that I haven't, because I didn't find I didn't find statistics of the new weight with ages, because, but yes, it should be checked if it's consistent or not. When I tried to do it, the calculations a bit by hand, it was quite consistent, actually.
Okay, good.
May I also have a question, please?
Yes, sure.
Tamás Bíró here. I wonder whether this exponential rise with the age, is it true for all fatalities or only for the COVID-19?
Oh, probably it will be. The problem is that there are not, I was trying to find the same thing for the flu, the seasonal flu, because I suppose, I mean, obviously you don't have the same chances of dying from this. But normally it's not, I mean, the statistics are not done very well in function of age. I mean, they will be what, this is not my field, so I don't know, but it's, no.
Yeah, because I've heard that for the Gompers distribution, you would expect exactly that. For example, from some insurance company modeling.
Oh, okay, yeah, this probably is. Yeah, I mean, I'm not saying that this is just COVID. I'm just saying that at least my support was that it doesn't really make sense to put it as a whole. Yes.
Thank you. Are there other questions? I think this was a very interesting discussion.
Okay,
there's a lot of
stop sharing.
interest.
Sorry. Yes.
So yes, so let's thank Beatriz again. And let's move to the next talk. That is talk presented by Nikolaos Fytas from Coventry University. It's a different topic. He will speak about evidence for supersymmetry in random field Ising model at d equal to 5. So, Nikolaos, are you there?
Okay, yes, I'm here. I guess you can hear me. Let's see if let me share my screen. Is that okay?
Yes, you can go full screen. Yes.
Okay, right. So, okay, in contrast to the previous talk, I will not be talking about mortalities and probabilities of dying, something way more boring from my side. So I would like to thank the organizers for their great work under these new difficult circumstances. And also to present the work that I have done over the course of the last few years on the random field Ising model with my colleagues, Victor Martin Mayor from Madrid, Giorgio Parisi from Rome, Marco Pico and Luca Lasoulas from Paris. More information about this model and some other relevant stuff can be found here in my webpage at Coventry University. So, yeah, why disorder systems? Well, we all know that basically disorder, not only in the framework of statistical physics, but across all the areas of physics, describes new phenomena and has fascinating interdisciplinary applications. And however, no matter how nice this may be, well, nothing comes without a price in life. And this is also the case for disorder systems, where a number of challenges, not only in the physical part, but also in technical terms, sometimes cast a very cloudy shadow in their study. For example, if we think about the theoretical approach to the problem, in most cases, criticality cannot be inferred from the pure counterpart of a disordered system, and mostly because non-perturbative phenomena that do not allow the approach from the perturbative point of view from the relevant clean system. Now, then if we look at the experiments, again, you know, the slow dynamic evolution of the system, what is known as a glassy behavior in the field, renders the performance, but also the deciphering of these experiments as a very questionable task, even for the most experienced experimentalists. Now, in this quite perplexed situation, we can say that the numerical methods, at least sometimes, appear to offer a deus ex machina, but this may not be seen as a panacea, as a solution for all the problems, because even in that case, one has to deal with some very difficult problems. So the first problem is that these disordered systems appear to have a ragged free energy profile, as it is seen in this plot here in the configurational space, where you see that you have many local minima, and therefore standard methods really fail to sample the phase space homogeneously. But even if we assume that you have a perfect code that does the job for you, then again, you need to overcome several barriers, like, for example, deal with statistical errors that are anyway inherent in these methods, also perform disorder averaging on the randomness distribution that you have, and then do also the extrapolation to the infinite limit size. And that can be a very tricky job. So basically, if one weights, on the same scale, the CPU cost that one needs to use and let's say the a priori expectation of arriving at a very safe result on disordered systems, he may find himself, sitting in a very discouraging situation. Anyway, however, we have decided over the last few years to deal with a very interesting model and fundamental model of statistical physics, the random field Ising model. And Martin Weigel already said a few things for that model yesterday in his very nice talk, but I would like to refresh a little bit your memory. So basically, the Hamiltonian of the model consists of the standard Ising term, where J is the ferromagnetic interaction, and these are the Ising spins. We are talking about nearest neighbor interactions, and that's a standard Ising term. And then you have another term, which is the random field term. These HX are the random magnetic fields, which can be drawn from some probability distribution. We will consider here distributions that have zero mean and dispersion sigma. Sigma now means the value, you can say the value of the random field, or otherwise the disordered strength. Now, before going into further details, the main thing here is to realize that at long length scales, the static induced fluctuations of the random field basically dominate over the thermal fluctuations. Okay, and this, if you want to write it down in terms of free energy, you would think that we know that in a pure ferromagnet like the Ising model, let's say the scale of variation of the singular part of the free energy is basically set by the temperature. But in this case here, it is set by this term, where sigma is the disordered strength, psi the correlation length, and theta is a new exponent that enters into the scaling theory of the random field Ising model and is connected with these exponents eta and eta bar, the two exponents that describe the decay of the connected and disconnected correlation functions. Now, also, this exponent theta is intimately related to the fact that we have a zero temperature fixed point scenario, as you may see in this renormalization group phase diagram here. Okay, so basically what you see is that you have, for sigma equals 0, you have the fixed point of the pure Ising ferromagnet, and as soon as sigma becomes non-zero, then the flow will drive you to the fixed point of the random field Ising model. So that's the normalization group flow. Also, something which is also very interesting to note is that the physically relevant dimensions of the model is basically 3, 4, and 5, so that there's no phase transition in dimension 2, and the upper critical dimension of the model is 6, meaning that at 6 and above we have mean field exponents. Now, this is very crucial. This RG phase diagram is actually very crucial, because it really helped us build on our numerical scheme, as you will see in a while. Now, the suggestion that the random field Ising model obeys at the critical point the supersymmetry came as a major surprise in theoretical physics in the 70s, basically. And one of the most important implications of this supersymmetry was given in a beautiful 2-page letter by Parisi and Surlas in 1979, who actually showed that dimensional is a property coming out of this supersymmetric formulation of the model. Dimensional reduction in this context means that the critical behavior of the random field magnet at dimension d and the critical behavior of the pure Ising ferromagnet at dimension d-2 coincide. Okay, and that was a major result at that time. Yet, in spite of the elegance and power of that theory, it was soon realized that the applicability is basically problematic, and there's an obvious breakdown here, because the three-dimensional random field Ising model has a long-range ferromagnetic order, whereas the one-dimensional pure Ising ferromagnet does not. Obviously, something weird was actually going on here, and in that sense, every perturbative prediction out of the theory of the random field Ising model should and must have been questioned all these years. And it is actually true that even questions like the concepts of like the universality, which is a very strong, it's a one of the major successes of the renormalization group, has been severely questioned for this model. In fact, there have been numerous numerical works that actually claimed that random field models with different random field distributions obey different universality classes. And as you may understand, this was a bit of a shock for the community, and also for the very fundamental field theory and the renormalization group theory, because universality is a product of the perturbative normalization group. Also, this fact of universality violation, together with the fact that we didn't have, let's say, a very strong command over the critical exponents that describe this model, somehow degraded the strong experimental interest of the model. Okay, and because this model is believed to be relevant to all these kind of condensed matter physics systems, somehow experimentalists would be very interested to have a set of values for the critical exponent. Now, in this sense, in order to answer, or at least move a little bit forward towards the understanding of these questions, one may resort, as we did, in computational methods. So in the last few years, we have developed a powerful panoply of simulation and statistical analysis methods that somehow set the basis for a relatively fresh revision of the problem. So the three main ingredients of our numerical scheme are basically listed here. So first, we use optimization methods, exactly like the ones that Martin mentioned yesterday. So we compute ground states at 0 temperature, of course, in polynomial time. And with this method, we avoid the thermalization problems, and also we can reach very large system sizes compared to standard Monte Carlo schemes. Secondly, we wrote down the fluctuation dissipation relations for the computation of correlation functions and the respective correlation lengths, of course, and also some reweighting techniques to facilitate our simulations. And finally, as a finite size scaling vehicle, we use the quotients method. So the quotients method is special in a sense because it allows us to have a transparent monitoring of the subleading scaling corrections, namely the exponent omega, which, as you will see in a while, plays a crucial role in unraveling the true asymptotic behavior of the model, and also provide us access to universal ratios. And talking about universal ratios, I show you here an example of the universal ratio psi over L, where psi is the connected correlation length here, and L the linear system over size, for the three-dimensional Poissonian random field Ising model, and for a set of different system sizes. So basically, the quotients method works exactly at the point where this universal ratio between pairs of system sizes crosses. Okay, and at that point, we compute the so-called effective critical exponents. So using this scheme, we basically studied the model at all the relevant dimensions that I said before, so 3, 4, and 5. And just in one slide, I would like to answer the first two questions about universality and dimensional reduction. But before that, I would like to provide an illustration here that actually shows, at least to my understanding, what has been the Achilles heel in the study of this model for many decades now. So if we closely inspect this figure, we see the Binder cumulant as a function of 1 over the system size. So the thermodynamic limit is marked at the 0 of the horizontal axis. And you see data for the 4D random field Ising model for the Gaussian distribution and for the Poissonian distribution. Now, if we assume that our work would stop here at a system size of the order of 32 to the power of 4, which is anyway not accessible at standard Monte Carlo simulations for dimensions, you would directly say that these two systems basically are described by a different universality class because their extrapolation would lead to different values. However, closer inspection, and given that we had the opportunity to perform very large scale simulations at much larger system sizes, you see that in the end, it's all about non-monotonic scaling corrections and a safe joint extrapolation to the infinite limit size. So this picture here, it was basically something that we've seen also in 3 dimensions, even more actually, and less in 5 dimensions. So basically, we have a non-monotonic scaling behavior and scaling corrections that we need to take into account. So the key ingredients of our scheme was that we have been able to simulate sizes of the order of 192 to the cube for the 3D, 60 to the power of 4 for the 4D, and 28 to the power of 5 for the 5D, which is really big. We performed averaging over 10 million samples, and we considered various random field distributions to answer also the problem of universality. Now, in the right hand side plot now, I show you an extrapolation of the critical exponent nu. So these are effective values obtained at different crossing points of the covariance method for the Gaussian and Poissonian distributions. And you see that like a joint fit produces like a single extrapolation to the value 0.626, which is very close to the value of nu for the 3D Ising ferromagnet. Obviously, we have done that for all the universal ratios and all the critical exponents, and that scenario has been verified. But I have chosen here to show you the value of nu for the 5D random field Ising model, because this is relevant to the dimensional reduction property that was discussed by Parisi and Surlas. Okay, so this is the first evidence that dimensional reduction may be restored at 5 dimensions. On the contrary, let me say that at 4 dimensions, our numerical results basically kill the scenario of dimensional reduction, because we get a marginally different, a very different value of nu. So like the full work that we have done is basically summarized in this table here. I know there are a lot of results, but let me just make, let's have a look diagonal and take, the key point, which is basically the following. So I'm showing you results for the 3D, 4D, and 5D random field Ising model, and also for comparative reasons, the 2D Ising ferromagnet and the 3D Ising ferromagnet plus the mean field results. Here is the set of critical exponents. Here are the critical fields. Here are the universal ratios and the exponent omega. And here is the verification of the Rushbrook relation. So 3 very important things. First of all, the exponent omega, as you may see, has a non-monotonic behavior as a function of the dimension. And the other crucial thing is that its value, at least in 3 dimensions, is very smaller than 1, which means that the scaling correction terms L to the minus omega are very important and should be taken into the scaling analysis. And this is something that hasn't been done up to this point. And also it may be behind these universality violations that have been questioned. The second thing is that the numerical results satisfy the Rushbrook inequality, because this has also been dissatisfied in previous works. And finally, let's select a few values. Let's say the exponent, the exponent nu, beta, and gamma, and basically compare the values between the 5D random field problem and the 3D Ising ferromagnet. And you see that basically there is some kind of nice agreement within the statistical errors. So this is, let's say, a first indication or additional evidence for the dimensional reduction being restored at 5 dimensions. Now, the prediction of supersymmetry, of course, go well beyond those regarding critical exponents. And they do involve both finite volume effects as well as higher order correlation functions. And here I want to show you that several non-trivial supersymmetry predictions are basically held at 5 dimensions, whereas they are not satisfied at 4 dimensions. So the setup that we used here was basically taking an elongated hypercube with periodic boundary conditions and linear dimensions L to the directions X, Y, and Z, and RL to the remaining 2 directions T and U. And R is what we call the aspect ratio, which is, of course, larger than 1. Okay. Now, let us also consider a point in the 5-dimensional lattice with these coordinates. So bold X will be the 3 Cartesian coordinates and bold U the remaining 2. The original arguments of supersymmetry have been set for the infinite limit size. Okay, but what we actually have in our hands is finite systems, and we wanted to find a way to basically transform all these relationships that the supersymmetry provides into these finite systems that are accessible to us. So basically, one can actually show that we can arrive to a so-called reduced supersymmetry where we can study finite systems exactly at the critical point of the 0 temperature fixed point, and by just taking this aspect ratio r to infinity, so that the natural variable in this case is this r squared. So in this sense, we can recover all the supersymmetric predictions of the infinite limit size just by using this reduced setup where only the 2 dimensions go to infinity. Okay, so this is something that we can actually check numerically. And some of the predictions of this reduced supersymmetry that we actually checked are the following. So first of all, one of the prediction connects the correlation function, the disconnected correlation function of the d-dimensional random field magnet to the correlator of the Ising ferromagnet in dimensions d-2, and z is some kind of normalization constant that plays no role. Secondly, there is the so-called word identity. So this is an identity that connects the connected and disconnected correlation functions of the random field problem, stating that if supersymmetry is valid, the 2 correlation lengths should be equal to that of the Ising ferromagnet. And finally, a little bit more complicated, one can actually estimate the correlation, the connected correlation function of the random field Ising model, which is also mapped to that of the pure Ising ferromagnet correlator in dimension d-2. So in the first plot here, what I show you is basically data of the connected correlation length over L for the 5-dimensional random field Ising model as a function of L to the minus omega, where omega we have used the value of the 3D Ising ferromagnet for different values of the aspect ratio. And what you see is that basically, even for r equal 5 or r equal 10, we see that we have a very nice convergence to the pure Ising ferromagnet value, which is given here by the dashed line. Okay, so first, I mean, we need to take the r to infinity limit, and then of course the infinite limit size. That's how we work in this reduced supersymmetry. So basically, we also take into account effectively the non-monotonic corrections by taking polynomials in L to the minus omega. And what you see here is that the extrapolation, we worked for the data r equal 5, because that was the case where we would actually reach the largest system size. That was 14 for the case of the 5D random field Ising model. You see that an extrapolation provides the value 0.642, and that is comparable to the 3D Ising model psi over L to an accuracy of maybe 1%. Now, additional evidence.
Sorry, 2 minutes before that, so if you can wrap up.
Right. So additional evidence are basically given by the disconnected correlation length over L. Again, you see here the extrapolation, the infinite limit size, and the result we get is quite comparable to that of the 3D Ising model. Accuracy check is basically of the order of 2%. And finally, we compare the Binder ratio, U4, for the 5D random field Ising model. Again, you see that the extrapolation basically takes us to the 3-dimensional Ising ferromagnet limit. And here the accuracy is even more when comparing these two values of the order of 0.2%. Now, as I promised you, I will show you that an unsurprising result, because we've already seen that dimensional reduction doesn't work at 4 dimensions. I will show you the same test for psi disconnected. Far away these values are from the value of the 2D Ising ferromagnet, also for the correlation length over L, but also for the Binder ratio. Okay, so this is just another verification of what we have previously seen in terms of critical exponents. So basically, to summarize, we have developed some new methods for the simulation and scaling analysis of random field problem. Our numerical results are basically consistent with universality, restoring, somehow clearing out a little bit of the cloud over the random field Ising model. We have provided high accuracy estimates for the full set of ratios, fields, and critical exponents, and also provided some evidence for supersymmetry and dimensional reduction being restored at 5 dimensions, but violated at 4 dimensions. And here I would also like to note that there has been some even more quite recent works in the literature that somehow confirm these results. So one is by the Ziltazous, Tissier, and Balog, a few papers. Another who used the non-functional renormalization group. Another work by Hikami, who is, I think, used the conformal bootstrap method and verified the restoration of dimensional reduction in 5D. And an even more fresh work by Kaviras, Ritskov, and Trevisani, where they used I think, the conformal field theory, and somehow provided again indications that there is a restoration of supersymmetry and dimensional reduction close to the dimension 5. And that would be all from me. Thank you very much.
Thank you very much. Let's applaud. We are a little bit behind the schedule, but if there is a short question, maybe we can take it.
If possible, I have a short one, Yuri Hulovac.
Hi, Yuri.
Hi, Nikos. Thank you for a very nice talk. You did it for different dimensions. Did you observe that certain quantities are self-averaging, whereas certain quantities lose self-averaging when you change dimensionality?
Yeah, actually, yeah, we didn't. No, we didn't check about self-averaging. I only checked at 3 dimensions, which was my original work, and there I checked the susceptibility and the internal energy, and I realized that the susceptibility is strongly non-self-averaging, whereas the energy is self-averaging. But to be honest, I have never tried to I have this data, but I never tried to actually use them as a function of the
Okay, thank you so much. Let's thank the speaker again.
Thank you.
And we can move to the keynote talk of today. The speaker is Professor János Kertész, which is a pioneer of network science, econophysics, and has been working on statistical mechanics on different aspects of it. And today, János, are you there?
Yes.
Yeah. Okay, thank you. Today, he will speak about a very actual question. And the question is, what do digital footprints tell about us? From the grammar effect to economics wrongdoing. So I'm really looking forward to the talk. Thank you so much.
Thank you, Ginestra. I would like to share my screen. Can you see it?
Yes.
Very good. Then I will go to this. Yeah. Now, let me see. Okay, it's not that simple.
Do you use Keynote or?
Just, no, I am using, okay. And I have lost the.
Yeah, maybe you can.
Can you tell me what you see?
We see the presentation layout with 2 slides.
With 2 slides, that's not the right thing. This is not what I want you to see. So let me try it again. And
no, it's again the same.
Again the same, but select. I thought I can select not the camera, but I can select the screen. But
sorry, János, I'm coming in. You have to put that in your PowerPoint presentation. So there is these options that you want to mirror your screen. So
okay, then I will just.
I'm trying, or you can just go on like that.
Okay, sorry about this technical
up to you.
issue. I don't want to take more time with that. So let me. Now you should.
Now it's perfect. Now it's the right thing.
Yeah. Sorry about that. So thank you, Ginestra, and I thank also the organizers for inviting me, and especially for putting together this very impressive and high-level conference in spite of all the difficulties. Of course, it would have been much better to be in person in Kolozsvár, but I very much hope for the next time. So today I would like to talk about basically sociophysics. That is the simplest title which I could have given. And review some of the activities we had in this field. This field has emerged from the early times of the new century. Due to the deluge of data, we have here an unprecedented amount of data at our disposal about people, about behavior, about how people move and so on. I think the term digital footprints was coined by John Bohannon in this science paper. And then I would like to read this quote from Nature 2007, where they discussed that traditional social science has problems with dealing with the questions in its focus. They can only scratch the surface, so to speak, in some cases, while being able to automatically and remotely obtain massive amounts of continuous data opens up unprecedented opportunities for social scientists to study organizations and entire communities or populations. And this has led indeed to the emergence of a new branch of science, which is now called computational social science. This is the famous paper by some of the leading personalities of this field, published in 2009 by Science. So what kind of data are we talking about? Well, this can be of very different kinds. It can be communication data, like call detailed records from mobile phones, or online social networks, or blog space, and so on. It can be mobility data. Again, mobile phones can be used to that purpose, or GPS data, or Oyster card type of data. Then, of course, publicly available data can also be included into the studies, like census data or public procurement data, commercial activities, credit card, point collecting card data, and so on. A very interesting direction is, which I will not be able to talk about today, is to study open collaborative environments like Wikipedia or GitHub, and many others like games, search data, surveillance cameras, satellite pictures, and so on. So this is really an enormous amount of data I'm sorry, about human behavior, human activities, which of course raise legal and ethical issues to deal with. Nevertheless, from our point of view, most importantly, these data mean a gold mine for science. So first, I would like to discuss a rather old piece of work which we did around 2007, where we tried to understand how the structure of the network of human interactions, the social network, the real one, is constructed, what is its composition. And for that, we used mobile phone data. And the reason why this may turn out as a good idea is that these mobile phones are extremely important in today's communication. I would say in yesterday's communication, because at that time when the data were collected, mobile calls were the leading communication platform. Of course, nowadays this is much more structured. And almost 100% of the adult population is covered and therefore one can assume that the communication network is or can be considered as a proxy for the social interactions. So the data we had comes from a European country in southern Europe, in south of Europe. I don't want to name the country, but you can guess which one was that. And we had at that time 7 million private mobile phone subscriptions from a provider. And what we focused on in this study was the voice calls within a home operator. And in this study, we used the aggregated data from a period of 18 weeks with, of course, anonymized users. And we require reciprocity. Of course, the calls are directed because somebody calls another person, but we requested reciprocity for the existence of a connection, and that was because we want to get rid of spurious links. In fact, the provider gave us private calls, but in spite of this intention of the provider, some of the users turned out to be business users and call centers and things like that, and that could be filtered out by this very simple method. So basically what we have is depicted here. We have here 2 users, and X called Y for 5 minutes during that period, and Y called X for 15 minutes, and that we merged into one single undirected link with a weight of 20 minutes. So we have a weighted undirected graph, and this is how a very tiny part of it looks like. And this network turns out to be a small world, as expected, I could say, and we wanted to understand the structure of it. And of course, we were not the first who were interested in the structure of the human social network. There is a very famous paper by Mark Granovetter in 1973, which has the title Strength of Weak Ties, which focuses exactly on this question: what is the structure of the human social network? And in order to make a strong hypothesis about this structure, Granovetter had to introduce the concept of the strength of a tie, which according to his definition, this is a quote from his paper, the strength of a tie is a probably linear combination of the amount of time, the emotional intensity, the intimacy, mutual confiding, and the reciprocal services which characterize the tie. I love this definition because I have been all the time puzzled what linear combination of emotion and intensity and intimacy means. But anyway, I think everybody understands what is the intention of this definition. Okay, so having this definition, he can make his hypothesis, which is as follows: the stronger the tie between A and B, the larger the proportion of individuals as to whom both are tied. And this is a microscopic or a local definition or hypothesis about the local structure, but it has severe consequences on the large scale, on the macro scale. Namely, if that is true, then the consequence is that a society consists of strongly wired communities linked by weak ties. And that is how the title of the paper comes from. And I should say that this is an extremely important paper, one of the most important papers in sociology. It has collected more than 57,000 quotations. So, but we have a network which is considered to be the proxy of the social network, and it is a weighted network. So we have the strength of the ties, and indeed, Granovetter's definition for the strength of the tie is closely related to the weight we can assign to the links. Namely, if somebody spends a lot of time or calls many times another person, then that means that this person invests money and time into this relationship, and that is very much in overlap with what Granovetter said. So, having this proxy, we can test Granovetter's hypothesis. And for that, we have to put things into mathematical form. And in order to do so, we define the relative neighborhood overlap. And that is, as it is shown here, oops, as it is shown here, you can see this formula. OIJ is this overlap, and and KI, KJ is are the degrees respectively, and Nij is the number of overlapping neighbors, of common neighbors. And this little figure illustrates how this concept works. If there are no overlapping neighbors, then the overlap is 0. If everybody overlaps, then it is 1. So all what we have to do is to measure the overlap as a function of the weights. But instead of the function of the weights, we measure the overlaps as a function of the cumulative link weight, in order to see how, to what extent, to what percentage the Granovetter hypothesis is true for this network. And here is the result, and you can see that Granovetter's hypothesis works quite well. It predicts a monotonic relationship between the weight and the overlap, and up to 95% this monotonic relationship is working. Beyond and for the last 5%, this is not true, and we do understand what happens there. I don't want to go into that, but in fact, what we can say is that our results give proof for the Granovetter hypothesis for this network. The blue curve is the empirical curve, is the curve which was calculated based on the core network, and the red curve is what happens if we randomize the links, and of course then this relationship between weights and topology disappears. So indeed we have also this community structure which was predicted. We have the strongly linked communities, and they are connected by the weak links. So we have here an example for a local property which has global consequences, or a micro-macro relationship, which is of course of high importance. But of course, such a structure has also an effect on the dynamics. Spreading is one of the most important dynamic processes which can happen on a social network. So it is an interesting question to see how these features of the social network influence spreading phenomena. And in order to do so, we did several studies. In the first case, it is a very simple toy exercise. What we did was the following. We took the network as it was and assumed a spreading process, the simplest one, which is an SI process. You start a process at a node, and then with some rate, this node infects neighbors, and this process goes on. In the first case, or in the empirical, as we call empirical case, the rate of transition is made proportional to the weight of the link. So if people talk a lot or for a very long time, then and the transition is more probable. While in the reference system, we took just the same value, which is the average weight. And here is what comes out. You see in blue again the empirical case, and in black the reference. And the black spreading is much, much faster than the blue one. So what we see is that this relationship between topology and weights has a slowing down effect. And the figure on the right explains what happens. You start the process from a node, and then of course very quickly the information or the disease or whatever spreads through the community where this selected node sits in. But then, since the links between the different communities are weak, it takes a lot of time until it is transmitted to the next community. Whenever that has happened, then of course again a fast period sets in, and so on. And this stepwise spreading is much, much slower than the case when you have the same rate for all links. But of course, the process, these calls, do not follow a simple homogeneous Poisson process. And this video is to show you what happens in reality. I hope you can see the video, where the red links mean phone calls, and the blue links mean text messages. And down here, you can see the time as it goes. And what you can immediately see that this is not a homogeneous process. First of all, you have daily patterns. For example, now nothing happens because it's night over there. But then as time goes on and people wake up, they start making phone calls. There is also a weekly periodicity because people, and this is shown here, people, especially young people at Friday night, make a lot of interactions and so on. But even if you deseason these data from these periodicities, you do not get a Poissonian process because there is burstiness involved. And this burstiness can be best shown by studying the inter-event time distribution, as it is shown here. And the inter-event time distribution for a Poisson process is in this log-log scale, just like this. But we see that there is strong deviation from that. There are parts of this distribution which are linear in this log-log plot. So it is a fat-tailed distribution. So the question, and of course there are also correlations because A calls B and then B uses this information and immediately calls C and so on. So there are further correlations also involved. And of course, it is a very important question to see what all these deviations from the Poissonian character of the process impact on the spreading process and the spreading phenomenon. And this is what we studied in detail. We introduced a large number of null models by different types of shuffling the links and shuffling the weights and so on. So by doing that systematically, you can switch on the different type of correlations one by one and arrive at this plot what we have here, which is again an SI model again on the Cole network, but in this time we use the timestamps of the interactions. And this curve, this red curve, shows the, let me see, the red curve is when we use the network as it was and the timestamp as they occurred. So that is a simulation with the empirical data. And the other curves come from the different types of shufflings. These are the different types of null models characterized by different types of interactions. So, for example, just to give you a feeling about that, I don't want to go one by one through because that would take too long. But we can take the same network in the sense that we use exactly the same network topologically, but and there is then an activity pattern on each link, but we can shuffle these patterns randomly. And in this case, of course, we destroy the correlations, these induced calls. We destroy the link weight relationship, but we do not destroy the link burstiness. So you can play around with this, and in this way we could figure out what the main effects on the spreading speed is. And this is summarized down here. What we see is that there is a slowing down. So whenever we switch on some kind of correlations, the spreading gets slower. So if we have communities, alone this fact introduces already a slowing down. If we have the Granovetteri link topology correlations, that is an additional slowing down. If we have burstiness, that again, in addition to that, slows down the process. Surprisingly, other effects like the circadian effect and other periodic patterns, or the temporal motifs, these induced correlations, they have no strong effect on the spreading speed. So that is about spreading using the mobile phone data. But in fact, the mobile phone data are much richer than just telling us information about calls and their times. And that enables us to study the egocentric networks of the social network, about which we know a lot, again, from social scientists. And this is a plot taken from Robin Dunbar, which tells us about the structure of such an egocentric network. The ego is sitting in the middle, so to speak, and it has these concentric circles of relationships. And as you go farther and farther, the intensity of these relationships decays. Dunbar says that these boundaries of the layers is rather sharp. This is not yet, according to my opinion, is not yet fully established hypothesis, but certainly it is true that there is this decay. And famously, Dunbar had this by now well-established statement that we have a finite number of real social interactions, which according to him is around 150, where people within this circle are such that we have real social knowledge about them. When we meet them, we can immediately start a conversation and so on. Of course, we know much more people, but this is the Dunbar circle, and the Dunbar number is 150. So the question is, can we learn something about the innermost circle using mobile phone metadata? Because we have metadata in the mobile phone data, which is, we know gender, age, zip code, we know most frequent positions, we know the device type, and things like that. And that enables us to look a little bit more into this network. And this is a figure which was obtained using some of those data, gender and age. And you can see here with blue the male and with red the female users. The gray users we don't know, because it's not that we know all these metadata about everybody. And the numbers on the links are the number of calls. And looking at such a figure, you can immediately tell a story. This is a couple, most probably, let's say husband and wife, and they have 2 children, a son of 20 years and a daughter of 23. And the daughter has a boyfriend who is also a friend of the son. And of course, the most vivid interaction is between this couple. But we also know that this large amount of calls happen only on work days, because on work days, this guy goes to a place probably to study very far away from where this girl is. And on the weekends they meet, they don't have to call each other. So these are stories you can immediately tell just by looking at the data. So what we were interested in, what we were interested in was how this innermost Dunbar circle looks like. How does the relationship change with age and gender? And ambitiously, we also think that when we find something characteristic, then that should be related to the very nature of humans, maybe related to our evolutionary history. So in order to be able to study that, we have to introduce a gender variable, where we choose +1 for male and -1 for female, and I apologize for that. It could have been the other way around. And this is what we get if we study, for example, the average gender of the best friend of an ego, where the ego's color is shown here. So this is the average gender of a male ego. This is, for example, the average gender of a 30-year-old man. So what is best friend? Best friend is, of course, not really the best friend. We don't know who is the best friend. This is the person in the call network whom this ego called most frequently. And what you can see here is perhaps not so surprising that the average gender of the best friend of a male is female, and vice versa. For a female, it is a male, especially in the young age. But then there are strange or not so expected differences. You can see that for the for the female ego, it crosses this 0 border, and that doesn't happen for the male. And if you look at the second best friend, which is shown here, you can see striking differences. The second best friend for young ages is of the same gender as the ego. And then again, there are quite characteristic differences between the male and female egos. But we can also break down these data according to the age and gender of the alters, of the partners of the ego. So these plots show, for example, 25 years old male distribution of best friends. And of course, some of the best friends are males, some of them are females. The females are much, much more than the males. You can also see some fine details that the female best friends have a younger age than the ego. And so the peak is shifted a little bit to the left. You can see also a second small peak, which is one generation apart from the ego's age, and you can see the same for female ego. Again, the best friend are, the peak is shifted to the right for the young age, and again the second peak can be seen. But this changes dramatically if you look at people apart from the previous one by one generation, or more or less one generation. You can see that now the ego's gender is around here, and this is a male. Still, the male ego has the partner as a best friend in quotations, but a second peak, namely in the generation of the children, emerges. And here we can see already a little difference, namely the female ego has a higher peak for the daughter. And here is summarized what you can see. During the reproductive period, women invest more in creating and maintaining pair bonds. So we could see that this peak is fatter, and as they age, their attention shifts to their children, especially to their daughters. And that can be explained by the arrival of the grandchildren. And this is related to what is called a grandma effect. The grandmother hypothesis, as shown here down, says that caring about grandchildren evolutionarily explains longer lifetime of females. It is a big puzzle for biology, how that comes that for humans in all cultures, in all countries, females live longer than males, especially that they live much longer than their reproductive period. And this grandmother hypothesis is a trial to explain how that comes about. And for men, the preference for the spouse remains, and there is no gender discrimination for the children. So you can see that this effect increases when you shift the ego's age by 10 more years. Then the female ego has a real preference for the daughter with respect to the son. So of course, as I already indicated at the beginning, mobile phones are not the only communication tools we have, and they are not the only modern communication tools. We also use online social networks. In fact, if we use only one channel information, as it is usually done, then we have a lot of bias. And we have a paper, which I don't want to go into now, which analyzes this bias. Okay, so what I would like to tell you about is that these online social networks have an organic evolution. They are born, they grow and shrink, and possibly they die. And this entire mechanism or evolution is, of course, governed by human interactions. And we are lucky that we have a very good example for such a full lifetime of an online social network. And this is IVIV, the Hungarian online social network, which was launched in 2002, 2 years before Facebook. and it had a history. First, it was an elite club, so to speak, but then it was realized that it can be used for business purposes, and then Hungarian Telecom purchased it, and it was the most visited site in Hungary for 5 years or so. And it had, at its peak, it had 4.3 million registered users. And if you think that Hungarians in Hungary are less than 10 million, and Hungarian speakers around are maybe, I don't know exactly, 12 or 13 million, this is a very high number. And in Hungary, 3/4 of the internet population was connected to IVIV, and then it got closed in 2014. And here in this plot, you can see how the number of active users changed with time. First, we had a very steep growth, and then it went down, and of course got closed finally. And this is a fantastic data set. We have a name, age, gender, location, school, and so on. And in this study, what we were interested in, how this collapse happened. And here this plot shows you the number of registrations and the number of churning, and of course it went up very rapidly. Of course, at the end, even the number of churning goes down because the number of users is already small. So what is the origin of churning? Well, as everybody assumes, the main reason of the collapse is Facebook. But this is only one part of the story. So this external information is, of course, important. But there is also social pressure. If my friends leave the network, then there is no point for me to stay there, and I will also leave it. So this plot shows how Facebook killed basically IVIV. So first, the interest in Facebook was a linear one, and the Hungarian version of Facebook was launched in 2008. So first there was a very slow increase, but then a very rapid one. So what you can assume then, if the only mechanism was that people read about this and switch to Facebook, then the linear increase of interest would turn into a linear initial churning rate, and that causes a quadratic churning population. But we see dramatic differences. The churning is much faster. And the reason for that is this social pressure type of thing. Here we see the fraction of the acquaintances of a user active at last login. This is a double-peaked distribution, and depending on the number of friends, you have a peak at around 45, and if you have few friends only, then you leave the system already with all of your friends present. Of course, if you have invested a lot into this network, then it is much more difficult to leave it, and you leave it only when most of or half of your friends have already left. But if you are just playing with the idea, then you easily go to the other network. So here you can see this change in the peak position. So this video shows you the cascading process I was referring to, which is this induced mechanism. So here you can see how people churn, and then due to this fact there will be a loss of friends, and then this makes people again leave the network. And one can set up a model which incorporates these effects. We have done that with a very simple model where we used an Erdős-Rényi with some triadic closure and assigned a threshold taken from the observations and deleted nodes with linearly increasing rate, and then introduced this threshold mechanism. And what you can see is that by tuning a little bit these parameters, you can have a very nice overlap with the observation. So the conclusion of this part is that the collapse, this dramatic collapse, is caused not only by the external information, but also by these cascading processes. So in the last part, I would like to tell you a little bit about how one can use this type of information to study the origins of economic misbehavior. We have a lot of economic data around, from stock market data to input-output tables. And the question is, can we deduce human economic behavior? Especially we were interested in misbehavior. Namely, the rules society makes for the economy and its agents are often broken, as we all know. The UN estimates the worldwide corruption causing a damage of 3 trillion, which is comparable to the GDP of UK. And there are severe effects related: increasing inequality, decreasing social trust, and slowing down of innovation. The problem is that it is very difficult to measure corruption, because the parties are, of course, interested in keeping it secret. It's totally different from robbery, where at least one party is very much interested in making it public. Therefore, the usual way to measure corruption is basically survey-based. Corruption Perception Index of Transparency International, Control of Corruption Index by the World Bank. But recently there is a development in this field, because data-based characterization has become a very hot topic. It means that indicator flags are assigned to public procurement calls. For example, what kind of flags that could be? For example, a single bidder, closed procedure, no official call for bids, extremely short deadline, and things like that. You can imagine what kind of irregularities could raise the suspicion that there is something wrong. In fact, this way you cannot indicate corruption, but you can measure corruption risk. What we know about corruption is that corruption is clustered in space. There are regions or countries or parts of countries where corruption is very high. It is persistent across time, and it is very difficult to find, irrespective of political or economic incentives are taken. It is very difficult to find. And that indicates that corruption is a social fact. And that made us to ask whether there is a relationship between social structure and corruption risk. And we can measure corruption risk from this public data on how towns awarded the contracts. The public procurements are about road repair, garbage collection, and so on. And we use this indicator method, and we can quantify social structure using data from IVIV. So basically this study tries to combine these two data sets. What can we say about the relationship between social structure as deduced from IVIV and corruption risk as one can learn about it from the public procurement data. And well, these are the data. So we have in Hungary 20,000 local government contracts in this period of time. And we selected only those towns which had more than, or at least 5 contracts per year. And we use these 2 indicators, either a single bidder or closed procedure, or the second indicator was a composite type of index. And here is the distribution of town averages. You have this closed procedure or single bid and the other index. So it shows a broad distribution. There are towns which have less corruption risk and others which have higher. So this plot is to show you that these indicators may have something in them. My Hungarian colleagues, but maybe also others, will have known about the Elios scandal. And we looked at the indicators in the Elios scandal towns, and there is a significant shift to the higher values in these indicators if we take this Elios scandal. The Elios scandal was a scandal where the son-in-law of the prime minister was involved, and the international watchdog of corruption have indicated that something wrong has been done, but the Hungarian authorities have not done anything. So corruption and social capital, that is what we are interested in. And let me jump this slide and come to the next one. There are 2 kinds of social capital, because social capital is something which somehow characterizes the structure of the society. A bonding social capital is extent to which people form very close, dense, homogeneous groups. So the mafia, for example, is a closed group. It has a very high bonding social capital. And the advantage of such bonding social capital is that there is trust, support, and it is easy to enforce norms. But it has also disadvantages. Group thinking, exclusion, it's very difficult to get involved. And again, norm enforcement, my example with the mafia is to be taken, can be also negative. In a city where bonding capital dominates, the society is fragmented into small, compact groups. So how to measure bonding social capital? Well, this formula should be familiar to the network people. This is just the expression of modularity, as we can measure, for example, from the Louvain method. But one can also calculate the maximum possible value. And we say that fragmentation is the ratio of these 2. So this is how we measure fragmentation. And here you can see a fragmented and a less fragmented situation. And the other type of social capital is bridging social capital, which is diversity. That is also a kind of capital if you know many diverse people. And the advantages are you can get easier new information and fosters tolerance. But it has also disadvantage because this is not good for support in hard times. The connections are losing. So we measure this again by using modularity. But in this case, we included all the connections also outside of the town, and they took the average over all individuals within the town, and it took this modularity for the egocentric network. And here is an example where you have a diverse and a less diverse situation. Oops, this is something which I did not want. Yeah. Okay. So making the long story short, what we find is that corruption is more prevalent in towns with excess bonding social capital, bonding facilitates favoritism, group-based norms, and corruption is less prevalent in towns with excess bridging social capital. Exposure to diversity facilitates impartiality. And this is the proof of that. And as for social science papers, it is not a graph, but a table with little stars. Little stars mean here, I mean, these are the slopes of the fitted lines, and 3 stars mean significance at level 1%. So these results suggest why corruption is persistent and stubborn, because the social structure is very difficult to change. It also explains why top-down approaches don't work. And it also indicates how to help. We should influence the social structure. And of course, such an approach has limitations. Corruption is difficult to measure. This is just a measure of corruption risk, if it is not necessarily representative. And of course, we cannot speak about causality. So for the conclusion of the talk, it's not a real conclusion because I have spoken about so many things. I don't want to give a grand conclusion. All what I want to say is that computational social science is fascinating. It is a truly interdisciplinary subject. It includes social scientists, computer and data scientists, statisticians, and physicists, and all of them have their roles. And maybe the last example could show you that it is not only interesting, it can also be useful. And there are many, many open problems like fake news, opinion bubbles, algorithmic bias, one-channel information bias and matching data, the question of representative sampling, GDPR versus scientific interest. Actually, all the questions are related to that. How one can make data public, that is a really severe problem. And the real challenge is how a combination of traditional and computational social science could be achieved. And with this, I would like to switch to thanking to my collaborators who are listed here and to the funding agencies, and thank you for your attention.
Thank you so much. Big applause for János Kertész. Thank you so much for the very interesting and comprehensive talk. Are there questions or? I'm actually, maybe I can start. I have a question on this slowdown of the epidemic spreading.
Yes.
So I understand this is a very important result, but I would like, because now there is so much interested in, you know, biological epidemic spreading. So which is the situation in which you think this slowdown really occurred? So it's only for, I don't know, kind of opinion spreading, or is also for airborne disease, or is there, you know, some caution in this statement, or is it universal?
This is really a very complicated issue, especially that the models one uses are usually not perfectly reflecting the empirical situation. We had a paper on this problem when we studied the artificial networks with different kinds of temporal, artificial temporal networks. And we obtained all kinds of behavior depending on the fine details. What is usually missing in the models is that since we are not using here Poissonian processes, these are processes with memory, and therefore they are usually not in a stationary state. So stationary state calculations are not adequate because especially if we have a bursty time series where the inter-event time have a very broad distribution, and that means that the transition period to reach stationarity takes very long. So usually we are in the transition period. So I don't think that this is simply to answer this question. I don't think it is only related to opinion dynamics, not at all. It is related to the temporal character of the network and on the details of the temporal character. I would like to refer to a recent paper by Martin Korsai and his collaborators, which treats exactly this problem, how a temporal network with bursty character affects the spreading speed.
Yeah. I think I know this paper. So are there other questions? Or?
May I pose also a question if possible? Yes,
sure.
So, János, thank you very much for your very nice talk. You really showed us how much we can do with data, but you very carefully avoided to speak about social physics. You always used computational social science, but why do you have a rejection for the word social physics? Because that was a very old word.
Indeed.
Right? Of the century, they called already social physics.
Yes.
This kind of science.
Well, I am not extremely happy with computational social science, a term. And indeed, some people use the term computational physics. Others use digital sociology and all kinds of things. My impression is that the science paper, which I referred to at the very beginning, sort of broke the symmetry, and people gradually shift to computational social science. This is, it is not perfect. Nothing, no term would be perfect. If we call it physics, then maybe some of our colleagues from other disciplines wouldn't be so happy. And I think after all, the subject is really the society in this case. So I don't think this is a very important matter. And I just take, I'm swimming with the flow.
Thank you. Thank you.
Yes.
I would like to state a question. You said concerning the corruption in the society,
yes.
And you said there is no, you cannot expect a change top down.
Yes.
But you have to change the society,
yes.
the network.
Yes.
And do you have some indication what you have to change? How should the network rearrange in order to reach the goal?
Yes.
So there are societies without corruption or less corruption and so on. So.
Thank you for the question. Yes. First of all, as you corrected yourself, I don't believe in a society without corruption. But indeed, there are at least some places which I know very well where there is room for reducing. And I think our study points exactly to the direction of what should be done. How to do that is very difficult. And the time scale is also a very difficult issue because we are talking about changing social structures. But what should be changed is the following. If the society of a town consists of closed societies, closed communities, then that, and one of them gets the power, then that is very much in favor of corruption. So inter-community links are helping reducing corruption. The other thing what we think to be what we think to have shown is that if a society is closed as it is in a town, So people are only talking to each other and never go out and never make links to other towns or other societies. Then they are also more inclined to accept corruption. While if they make a lot of outside links, then they see other norms, other people, other practices, and then that could reduce corruption.
Yeah, thank you. Yeah, I think that's interesting. Okay.
Thank you.
Thank you. So thank you, János. Let's make a virtual applause again. Yes, so the next session is this cultural event. Yes. Yes, so let me look at the...
If you let me, Ginestra.
Yeah. Okay, thank you. Yes.
So thank you very much, Ginestra, for chairing this session, and thanks for all the speakers speaking here. It were really, really interesting talks. And as we promised you, in each afternoon, we included something about Transylvania, something to get you closer in this virtual place to us. And today is what we will prepare. What we prepared to you is something from art, and we want to bring you a little bit closer to the Hungarian arts and painting schools here in Transylvania. And our guest is an art historian who finished at the Goethe University of Madrid. She's Viktória Adrienn Barazsuly. She's here with us. And we thank her that she offered to present us some facts about the famous Baia Mare or Nagybánya painting school. And she's an expert in everything which is related in Hungarian art history here in Transylvania. So I give the word to Viktória.
Thank you. Thank you very much for this introduction. Maybe the expression expert in everything which is Hungarian art is a little bit too much, but I will try to present you this very interesting and colorful piece of Transylvanian cultural heritage, this School of Artists. I will try now to share my screen with you. Okay. And thank you very much for being here and for being interested in this other topic, and for being interested in knowing a specific artistic movement which was here in Transylvania. And the people from Nagybánya, Baia Mare, would say that is even present today. The idea of it is present for sure. But what is exactly this Nagybánya or Baia Mare? If I am right, you already know that Transylvania had a really interesting history. So from time to time, the countries changed, the borders changed, the places remained the same, but other names were given to them. Well, Nagybánya is actually a town in the northwestern part of Romania with a population of almost 140,000 people. Nagybánya is the Hungarian name of it. I will use this one. Nowadays, the official Romanian name is Baia Mare. So this is how you can find it on the map. It is surrounded by mountains, which is very important from our perspective, because these mountains are present in most of the Baia Mare or Nagybánya paintings. It was first mentioned in a written document in medieval times in 1328. in a document released by Charles I of Hungary, and some years later, it is already mentioned as a very important medieval town with a mining industry. Hence the name Nagybánya. It means big or great mine, and roughly the same in Romanian. Gold was the most important element mined here. Nagybánya was the most important source of gold in the Hungarian kingdom, but they also had other activities, other kind of mining activities, for example, iron. The climate is also a very specific one. It is a Mediterranean one, and it is therefore the northernmost reach of the chestnut tree, which sounds like a silly detail, but it's also present in the pictures, in the paintings later painted by these artists. And Nagybánya is, of course, also a place, a town with very interesting landmarks, which can be also found in these pictures and which identify very precisely the town itself. The first one, the medieval tower, is the so-called St. Stephen's Tower. This is the only part of the Gothic church which stands today. They built a church here in the 1300s, a very huge one. But unfortunately, during the very turbulent historic times, we cannot see it today. The other church in this picture, the one with the red cupola, is the Calvinist church, also present in many paintings. And of course, the specific architecture of this place, very specific houses, the marketplace, and everything can be found in the paintings later. And Nagybánya, as mentioned in the title as well, is an artist colony, a school practically, which has a very long tradition. Everything began in 1886 with a painter called Simon Hollósy, a Hungarian painter, who opened his school in Munich, Germany. I will give you now a timeline of all the events, and later I will present some more in detail some of these painters and their work. So this Simon Hollósy opened his own school, art school there in Munich. He studied and lived there, and from time to time, several young artists from Hungary came to him, studied with him, stayed with him for some months, and then came back to Hungary. And then in 1896, he himself, together with some other friends and pupils, former pupils of him, founded the Nagybánya Artists Colony. These were Hollósy himself, and some other names, Ferenci, Réti, Torma, and Iványi Grünwald. They were the founding members of the Nagybánya Artists Colony. Some years later, Hollósy left the school, and the four other masters started another form of being together with the students, of teaching. And then around 1906, a second generation emerged. There was two groups of them, and the first being a traditional group of students, of pupils, who stepped in the footprints of the old masters and followed their rules, their ideas, not rules. And there were the so-called neos, the new generation with the new ideas, who were the rebels of the school. And I will show you the pictures, and you will find out why. Their painting, their art was completely different from what was present in Nagybánya until that point. In 1911, another institution was founded in Nagybánya, the Association of Painters, which was important from this institutional point of view, because until that point, this school was a rather loose institution with not so many rules, a very free environment without any institutional background. But then in 1911, this association was founded, and later it was very important because it could make the connection between what was before the First World War and after the First World War, when everything changed. During the First World War, there was silence in Nagybánya. Only a few painters stayed there, but of course, those were turbulent times. Traveling was very difficult, so not so many painters present in that period there. In 1919, Torma reopened the school. Thanks to this association, he could prove that it truly existed with an institutional form before the war. So even if the country changed, if Nagybánya, which was part of Hungary, after the war became part of Romania, the school could continue. And they accepted students also from other parts of Romania, from Bucharest, for example. Many students came and studied under his brush. In 1927, another leader, Mikola, another painter, became the leader of the school. And then in 1937, the Association of Painters of Nagybánya broke off. So the great period of Nagybánya ended. But nonetheless, after the Second World War, some kind of rebirth took place there. And even during communist times, it was a very strong artistic center in Nagybánya, and it is even today. Let's clarify a little bit the beginnings and Hollószy's background, because this is important for us to understand why Nagybánya was, let's say, revolutionary place in Hungarian art, and not only. And I also would like to put emphasis on the international character of this school. You will see later. So Hollósy studied and lived and taught in Munich, in the Munich School of Arts, which was an academy of arts, where this painter called Wilhelm Leibl was the leading figure. As you can see in these pictures, he was interested in genre painting, everyday scenes, light ones, not with a deeper sense for social dilemmas or social problems. These peasants are painted here as if they were actors in a play. They are presented with big contrasts, so in a very theatrical way. So this was the major style there in Munich. This style was taught also to the other painters. And then small revolution, but very big change came with the presence of Jules Bastien Lepage, with this painter who, compared to Wilhelm Leibl, had a completely different way of painting. He also painted genre painting, so everyday life, but in a completely different manner. You can see that the lighting is totally changed. Everything is lighter, brighter, although the color palette is rather pastel, so silverish. But everything feels lighter. The accent is in the exterior and not on the interior, on the depiction of interiors. He was a leading figure of naturalism, which, in contrast with romantic painting, thought that painting everyday scenes and nature as we actually see it is more important than painting, for example, historical scenes, which are very, very, very finely composed, and which are very, have this very extreme visual image. Instead, everyday life, everyday nature is interesting. The ordinary is interesting, even if sometimes it is ugly. So without any idealization, everything as it is. This is not yet impressionism. Impressionism, that comes a little bit later, and it's different. This is only life as it is, nature as it is. And if we compare a very successful painting of Simon Hollósy, entitled The Kiss, with a painting of Wilhelm Leibl, we can see that the pictorial quality is very, very different. Everything is lighter, brighter, full with warm, velvety textures. The scene itself is lighter. However, Hollósy is not very interested in the deeper problems of the peasants, let's say in this case. The theme here is rather an anecdote, very light. The kiss, the boy is stealing a kiss from the girl. But the quality of the painting is different, and the eye of the painter is different. What he wants to show is very, very different of what happened in Munich in those times. And the big change came after that with a commission. Hollósy was commissioned in 1896 to paint the ruins of the castle of Hust, Hust being a place not very far from Nagybánya. And this is the painting he made. And this changed the course of Hungarian art, because he was fascinated by the nature he saw here, by the landscapes, by the scenery he saw here. And since he had two friends and former pupils, Torma János and Réti István, who were from Nagybánya, they were born there, he told them to help him organize a summer school there in Nagybánya. And so it happened, and in 1897, the first year of Nagybánya painting started. But before we get there, let me just point out that if you look at this picture, at this painting, although the main theme should be the castle itself, the ruins, it should be, like a historical painting, but it is not. The primary theme became the nature, the landscape itself, the hill, the little houses, the green, all kinds of greens. And the castle is just like an apropos, like to paint the nature itself, to paint the scenery itself. And this will be a characteristic of the Nagybánya artists: love for nature, love for landscape, and trying to find solutions how to paint it as it is. The school, Nagybánya is also a school, of course. And how was the school organized? First of all, it was a so-called free school or free academy, which meant, this was actually a typical form of studying arts, mostly painting, but not only, also sculpture and ceramics were studied in Nagybánya. This meant that there was no formal education. There were no classes, nor theoretical studies. There was also painting, only practice, students who painted, and masters who corrected them. As you can see in these old photos, the painters are just standing there painting, masters are wandering around them and making all kinds of correctures for them. So it was a very practical way of studying painting. no previous studies were necessary to go to Nagybánya, so everyone who wanted to learn, who wanted to study, could actually go there and learn from the best painters in the whole country. As you can see in these photos, there were lots of women who studied there, who spent their summers there. Unfortunately, we know almost nothing about them. No official records remained, mostly because of this free spirit of the school. But I think it would be extremely interesting to know who were these painters, these women, and why we cannot see, we cannot know their works. The students choose their masters, so not the other way around. It was very democratic. And if there were persons with whom they could not work together at all, they could outvote them from the school, but this happened only 3 times during the history of the school. The city of Nagybánya helped the artists. It was really proud of the status of it, of the title of City of Artists or Town of Artists. So it helped them a lot. The mayor constructed different sheds for them, later studios, ateliers, even donated from time to time paint to them or brushes. And a very sweet little detail, the train ticket was for free to them, for all the students, all the painters who had to travel from one location to Nagybánya by train, of course. The train was free for them, so they could, this was not a burden they had to carry. However, they had to pay in for the payment, for the fee of the models, because they had to be paid. And in the very beginning, it was really hard for the artist school to get models, because the people from Nagybánya, well, they didn't really want it to be models for these paintings. And of course, being a model for a nude was absolutely out of question for every person, woman or man who wanted to remain respectable in the society. So it was really difficult to get models, especially for nude painting. But as you can see in the photo, they could find people who were willing to pose as models for a fee. Although the fact that landscape was the most important theme, they studied all kinds of painting. So also nude painting or still life or even historical scenes were present in Nagybánya. One could ask whether Nagybánya, this art school, has a specific style which can be, identified easily when you look at a painting or not. And the answer is no. Nagybánya is definitely, it is not a style. Here you can see 2 paintings from the Nagybánya artist colony. They are completely different, no resemblance at all. The first one is the painting of Ferenczy Károly, one of the founding members. The other one is a painting of Czóbel Béla, who was one of the neos, so of the rebel ones, completely different, although the main problems are similar. The light and how the light changes. How can a different lighting change the colors of leaves, the colors of the surface, different surfaces, and the shadows? What color are the shadows? How can you capture the ever-changing light? The problematic is the same. The way they answer it, the solution is completely different. Here also, another painting by János Kertész, where he wanted to capture the lights coming through the flowers of two trees, how they change the color of the grass. And there is a very beautiful contrast between the green of the grass and the brown of the soil next to it. And this dynamic between the horizontal and the vertical lines is really, really pretty here. Painting plein air, so in the plain air, in nature, actually, was a novelty in those times. So at the end of the 1800s, painting in nature was a novelty also in northern, in the western parts of Europe, and especially here in Hungary. It was necessary for it a different way of painting. Before, you could execute very, very fine work in a studio because everything was, constant. But in nature, everything changes so quickly. The sun goes down very quickly, or it moves. Everything is different. Then a cloud comes in. Then again, everything changes. So you have to be very quick. Your brush strokes have to be very quick. And the painting is your eyes have to perceive all these changes very, very quickly. You have to adapt. It is very dynamic. And therefore also the paintings are very dynamic in themselves. And the visual aspect becomes very primary. The colors, the pattern of paint, and all this kind of very this other type of harmony, which doesn't come from very fine brush strokes, but exactly the opposite of it. Or here, this painting of Samu Börcsök. He loved studying haystacks, and here is a painting of haystacks in winter. Again, the shadows. What color are the shadows? Here they are bluish, and also this novelty that the shadow doesn't have to be gray or black. It can be lots of colors, because in nature you can rarely see true black. And here is a very extreme example of the style. Vilmos Huszár is a painter who also studied in Nagybánya. At the beginning, he painted like that. And then later, he became a very modernist artist, part of the style group in the Netherlands, in Holland. So yeah, Nagybánya is not a style, but a starting point, which is very important. And it was an extremely good study place for all the painters, which gave them the necessary skills which could then later be developed. Everyone could have their own style there in Nagybánya, so the masters were not very strict in questions of style. They had other kinds of remarks with which they helped the students. And of course, Nagybánya was also a theme for these paintings, with all those landmarks I mentioned before, and which can be identified very, very precisely, as shown in this slide, or in this one. And of course, it's very interesting to compare how all the different painters showed us a theme, a subject. And yeah, how many artists? Well, more than 400 were present there in Nagybánya, of course, not at the same time. There were some who studied there only for some weeks, others came back from year to year. And now let's see some of the painters and their paintings. I already mentioned Simon Hollósy, and I showed you this painting of him. And this is how he continued his interest. He was really interested by light coming through a window, light coming from the outside, and lighting the faces and all the different textures. And later, after he came to Nagybánya and later to other places, he became interested in nature, in the landscape, and in the ever-changing landscape. And here are some haystacks of him, which are rather similar to what happened with Monet in those times, for example. They are made roughly at the same period of time. János Torma, another one of the founding members, he started with also with a darker palette, darker colors, as the others, or as Hollósy himself, but he was influenced by Art Nouveau from the beginning of his career, from using decorative textures and backgrounds. Here the background is almost gold-like, and I love this contrast between the gold background and this blue painting the girl is resting her arms on. The influence of the Japanese prints can be observed here as well. There is no sense of space, no sense of perspective here. Everything is as it would be one flat surface. And this was because of the influence of Japanese prints, which are very loved in Europe in the second part of the 1800s. And they had a really strong impact on art itself. Maybe he was the most, maybe Torma was the most interested in social themes, in realist painting. Here you can see a scene in a cemetery, very poor people, and observe how the man in the front covers his nose because, you know, this very poor people smell bad. So this kind of realist painting, naturalism, painting everyday life as it is with all its problems and all its ugliness. So the ugly and the ordinary is also can be also interesting for arts and artists, and for Torma it was. But later, something similar happened as with Hollósy. His colors became more vibrant, the brush strokes lighter. Here everything is very realistic, like a photo. Here the brush strokes are very loose and rather large brush strokes. The colors are completely different, light, and he was very interested in how can you place a figure harmoniously in a landscape so that the landscape would not be dominated by that person in the picture. So somehow the person, the woman or the man becomes an integral part of nature. István Réti, he was a very important teacher in the art school, but he didn't paint lots of paintings. And he was also the one who wrote down the history of the artist's colony and of the school. He started like this painting with small cut interiors. He was also interested of light. What does light do with faces, with small places? How does it make these places more velvety and soft? And then later, his eyes opened, his cuts opened, the panorama opened, because he was also fascinated by Nagybánya and the landscape, and his greens are very specific to Nagybánya. That dark green he uses, it's nicknamed by art historian and art critics the Nagybánya green, because it is very, very specific. Károly Ferenczy was one of the other leading figures and founding members who started also, just like Torma, with Art Nouveau inspired painting, very decorative surfaces. I love this painting of him with the bright red flowers and the pale pastel colored women and background here. But this is one of his very well-known and very successful works, entitled Sermon on the Mount. He was an atheist, but he painted many biblical scenes because he wanted to emphasize his nature experience, which was almost religious-like. So he experienced nature as a religion, and that was the atmosphere he wanted to show us as well, with placing biblical scenes into nature, into color, into light. It is very interesting here how we become part of the group, how these figures are standing with showing their backs to us, as if we would be there as well. And that person in the middle is Christ. You can almost not see in his halo. So he is almost like if he would be a normal everyday man. And the people there, sitting there, are people of Nagybánya, peasants of Nagybánya and painters. And some critics say that maybe the figure of Jesus can be associated with Károly, with Ferenczy Károly as well, but that is rather problematic. This is a painting which doesn't really work on screen. You have to see it in person in Hungary, Budapest, in the National Gallery, but it is a very important one. It was not very well received during when it was first shown to the big audience, but it is very important because of how Ferenczy shows us light and color. It shows the three magi, the three kings, going to Bethlehem to greet Jesus Christ. They are in a forest, and I saw this in person, so I know what is the feeling. I'm just so sorry that you cannot feel it. The atmosphere is like a fairy tale, a very mystical one, but the whole painting is just like a feast of color and light. The green hues on the fur of the horses, the very bright red there in the middle, the velvety dress of that king. So everything, it dissolves in light, it dissolves in the atmosphere, in the air, and it becomes only a visual pattern, l'art pour l'art. This is what Ferenczy does really, really, really well. No narrative. It is just a pretext to paint pure visual imaginary. Other paintings of him, he loved also to paint, to place figures in landscape, which could be nature or a more domestic landscape, like this one in front of his house, with really beautiful contrasts of greens and reds everywhere. Béla Iványi Grünwald was also part of the founding members, but later he was influenced by the neos, by this younger generation of painters, and his painting changed from this very detailed, very fine, fairy-like, very soft, lighted paintings. He became more, let's say, modern, with bigger patterns of one color, bigger spots of one color. And for example, if we look at this picture of this painting of him, gypsy girls sitting on the side of the Zazar river, which is the river there in Nagybánya, we can instantly think of Paul Gauguin and his Tahiti pictures, Tahiti paintings. now I will show you some, really quickly, some paintings from the second generation. Jenő Maticska, who is part of the more conservative line of the second generation. András Mikola, also being part of the conservatives, but for him was very important, again, light and how the light can dissolve all the colors and change them. János Kertész, they say that he lived in Felsőbánya, which was the settlement right above the city, uphill. So therefore, he was the best at painting pictures, landscapes seen from above, from bird's perspective. And he was also interested in painting winter landscapes, showing the different hues the white snow can have. And then here are the neos, all those painters in the second generation who went on another path and who were very open to the neo-impressionism and post-impressionism present in Western Europe. And also the fauve painters. They used very bright colors, not naturalistic ones, but which could be used to express a different atmosphere, different feelings, different effects of light. I love this painting. It shows how the women come home from the forest carrying branches, and the sun is going down and everything is brighter in that golden hour of the evening. And if you want to compare to something in Western Europe, I show you here a painting from André de Rennes, again, a French painter from the Fauve group of painters. Or another painting of him, which is very, very close to pointillism. Again, another three women at the side of a river. And here I show you a parallel with Van Gogh. So this is what I would like to emphasize, that these people studied in Nagybánya during the summer, spring and summer, and then they went off and went to Paris, went to München, went to other parts of Europe and saw what's happening there, saw what kind of new ideas are present there in the arts. They were fascinated by them, and then they came back to Nagybánya and they implemented these new ideas and they tried them out. And of course, they had big conflicts with the old masters. And at one point, most of them, of the neos, went out from Nagybánya and founded another school, the Kecskemét Artists Colony, and other artist colonies in Hungary as well. Sándor Ciffer, he is very similar to what we can see on Matisse's paintings, flat surfaces, very decorative ones, a very specific sense of perspective and of depth, bright colors, expressive colors. Here, the Nagybánya landscape with the cross hill, the Kereszt hill, a very specific one. Again, through his subjective lens, using his bright colors to emphasize all what's happening there color-wise and light-wise. Csaba Vilmos Perrot, he was strongly influenced by Cubism. Here is a painting of Georges Braque, one of the founders of Cubism, and also Pablo Picasso, who had a Cubist face in his art. Hugo Mund with extremely beautiful greens, all kinds of greens, and heavily influenced. And David Jandi, who was a big, he loved the art of El Greco, and we can feel how his paintings were influenced by El Greco. So he was the one who looked in the past rather than in the future, but that was not a very exclusive case. So this was what I wanted to tell you in 40 minutes. I wanted to show you that this painting school was not something which happened very isolated, but it was something which happened in accordance to all the changes and all the ideas present in the art of Western Europe as well, which was a really, really big cutoff in this development was the First World War, because during those times travel was really hard. And later, when the historical scene changed, then these artists were not able to travel anymore to Paris and all the other parts where the center of art was. So maybe this very promising development was a little bit stopped. However, these paintings still are present in the galleries of not only Hungary, but also other parts of Europe, and they are very well sold during different auctions. And I think that they are very beautiful and they are worth knowing. Thank you for your attention.
Wow, thank you very much. That was a very relaxing presentation after so many physics that we learned today. And just to make you an image about how interested physicists are about this, you can see that Professor Ha-Won Jeong, who had a talk about analyzing with physical methods paintings, is here with us, although in Korea, where he's living now, it's midnight almost, so he's still with us.